Here's our product to sum formula for the sine of one angle times the cosine of a different angle. If I do some algebra with this, let's start by multiplying both sides by 2. You get this. Now, I'm going to do a little trickery here. It's not really trickery, and to be honest, I don't know who came up with this or how they decided to do it this way, but it works. So I'm just going to show you how it's done, and I'm doing it for this particular formula. We'll be able to apply it to some of the other ones later on. So if I take alpha and I call it u plus v over 2, and I take beta and I call it u minus v over 2, and then I go back into this formula and replace all my alphas and betas with these two things, it ends up looking like this. And now everywhere that there was an alpha, I'm going to put a u plus v over 2. U plus v over 2, u plus v over 2, u plus v over 2. And wherever there was a beta, I'm going to put a u minus v over 2. Why would I want to do this, you ask? That's a very good question. I'm going to simplify the right-hand side now. Notice that inside my argument for sine, I have u plus v over 2 plus u minus v over 2. Let me do that off to the side here. U plus v over 2 plus u minus v over 2. I have a common denominator, so I'm just going to add my numerators, u plus v plus u minus v all over 2. That's 2u, and the v's cancel. I have a plus v and a minus v, so I get just u there. So all of this mess right here is just u. And then I have the sine of, where shall I do this part? Try to squeeze it in here. U plus v over 2 minus u minus v over 2. Here I have to be a little more careful because I do have a common denominator. When I combine these, I have u plus v minus the quantity u minus v. So that's going to give me a u minus a u, so those cancel, and then a v plus a v, so 2v over 2, and the 2's cancel, and that gives me just v. So all of this turns out to be just v. So now I have this equation, 2 times the sine of u plus v over 2 times the cosine of u minus v over 2 equals this thing here. But if I change the order, the sine of u plus the sine of v, if u and v are not common angles like pi over 6 or pi over 4, right, or 3 pi over 2, but they are angles that when you add them together and divide by 2 become nice angles, then this is a nice formula to use. So if you have the sine of u plus the sine of v, you can find its value by taking 2 times the sine of the angle u plus v divided by 2 and multiplying it by the cosine of the angle u minus v divided by 2. So this is our first sum to product. There's my sum, and I'm going to turn it into a product. It's my first sum to product formula. There are others. I will list them here as I've been doing in all the other videos, but we'll work on deriving them in class. So let's move this up here. It's in parts again. There we go. And we don't really need this anymore. And I'll list the others here for you. Now, the first thing I've done here is to rewrite the first formula using alphas and betas instead of u's and v's. The u's and v's were just a convenient way to show you how we got the formula. But once we have a formula, we can replace the letter we use for the angle with anything we want, and it's going to hold true. I have the sine of one angle plus the sine of a different angle. This is the sine of one angle, is the sine plus the sine of a different angle. And as long as the u's and v's here get replaced in the same way as the u's and v's get replaced here, in other words, u for alpha and v for beta, or the other way around, as long as they're the same, then it doesn't matter which letter I use. And so I've done this primarily because when it lists the sum to product formulas, your textbook uses alpha and beta, and I want to be consistent. It really doesn't matter. You can use u and v, you can use x and y, you can use theta and phi. It really doesn't matter. I've just changed it because your book uses alpha and beta, so I wanted to be consistent. So with that in mind, here are your 4 sum to product rules. Now we're not quite done yet here, but let me point out the similarities and differences. This is the sum of 2 sines. This is the sum of 2 cosines. This is the difference of 2 sines. This is the difference of 2 cosines. The sum and difference of 2 sines both use sine, cosine. The alpha plus beta comes first for this one, and it comes second for this one. And that matters because the first factor here is a sine, and the second factor is a cosine. So here we're taking the sine of alpha plus beta over 2. Here we're taking the sine of alpha minus beta over 2. In the first formula, we're taking the cosine of alpha minus beta, and in the second one, the cosine of alpha plus beta. In the cosine plus cosine, the sum of cosines and the difference of cosines, we have 2 cosines and 2 sines. They both have a alpha plus beta first, and alpha plus beta, and then alpha minus beta second. The only thing that's missing here, and I left it off on purpose because I want to add it in a really bright color, is this minus sign. That's the only difference between, well, it's the only minus sign in all 4 of the formulas. So it's really easy to forget about it. It's the one that's the difference of 2 cosines. That minus sign does not occur in the difference of 2 sines. So it's really important to remember that. So I would write all of these down on your note card. This is another group of formulas that you're going to need to be familiar with. 1, 2, 3, 4. And let's take a look now at how you might use them. I decided for this one to do an example of a verify or proven identity. So I'm going to prove, and I think I'm going to start with the left-hand side here. I decided to do this problem because it just looked really intriguing. It looks kind of messy, but when I looked at it, I noticed something here. I thought, well, how on earth am I going to do with cosine cubed? And then I realized that if I broke up cosine cubed into cosine times cosine squared, I could factor out a cosine from this term and this term. So I'm going to start with that. So my left-hand side is 2 cosine cubed x minus cosine x sine squared. And yes, you have to copy it all the way out. And I'm going to rewrite that as 2 times cosine x cosine squared x minus cosine x sine squared x. And that's, boy, that's almost not even algebra. I guess it counts as algebra. I factored out algebra. I rewrote cosine cubed as cosine times cosine squared. Okay, and then, and I'm using square brackets here because I'm going to factor out a cosine, which leaves me with cosine squared of x minus sine squared of x. That is also algebra. Now, when I do that, I notice that I have something here that looks familiar. I've seen this before. It's one of my identities. In fact, it's the cosine of 2x. It's the double angle formula for cosine. So this is double angle formula. All right. Now, what I have here is a product of the cosine of one angle and the cosine of a different angle. Now, it's just x and then twice x. It's just a double angle, but these are different angles. And so I could use a product to sum formula here to rewrite this. So that's what I'm going to do. I'm going to rewrite it as 2 times, now so far all I've done is copy down this 2, okay? Now I'm going to rewrite the cosine of an angle times the cosine of a different angle using the product sum formula for the cosine of two angles, and that's 1/2 times the cosine of alpha minus beta. So the first angle minus the second angle, that's x minus 2x. And then I have to add cosine of alpha plus beta, the first angle plus the second angle. That's x plus 2x. This is a product, so these two things here cancel each other. And I get the cosine of x minus 2x, which is negative x, plus the cosine of x plus 2x, which is 3x. Now on the surface, it doesn't look like we're much farther forward, but one thing I can point out is that I know that when I plug a negative value into cosine, it's either going to spit out cosine of x or negative cosine of x, depending on whether this is an even or an odd function. It turns out that cosine is an even function, so this is the same as the cosine of x. Now I got pretty excited there, so I'm going to have to back up and put in some of my justifications here. I haven't been telling you on paper anyway how I got these. I used the double angle formula to get from here to here, because this right here is the double angle, the right-hand side of the double angle formula for the cosine of 2x. To get from here to here, I used the product to sum formula. So I'm just going to write product to sum. And then I did some algebra. All I did here was, I'll write it down first, algebra. I canceled the 2 here. I reduced the fraction 2 times 1 times 1 times 2, which is 2 over 2 to 1, right? I reduced that. So technically that was algebra. The other thing I did was combine like terms here and here. So I just used algebra there as well. And then cosine is even. That tells me how I got from this to this. I didn't change this term, but I did change this term. So far what I have is that this left-hand side, this messy left-hand side, can be written as this. That's not quite so bad. And I was just thinking, I'm really not sure where to go next, but as it turns out, that's exactly what I was looking for. It's in a slightly different order, so I am going to rewrite it as cosine of 3x plus cosine of x. That's just algebra. And now it is identical to the right-hand side, so I'm done. And that really wasn't so bad. I did have to use a couple of different identities. I used a double angle formula to rewrite this part. No, I used the double angle formula to rewrite this as the double angle. And then I used the product of these. I'll put a dot in there for times. This was a product, and I turned it into a sum. And then I did some algebra here, simplified it to this, and then an even odd identity, the fact that cosine of negative x is equal to cosine of x. And then the rest was just sort of algebra, and it really wasn't too bad. Now, this video's getting a little long, so again, I'm going to say don't feel you have to watch the second half or the next part of this video, but I think what I'm going to do with the next one is the same problem. I'm going to prove this identity, the same identity, but I'm going to start with the right-hand side. And the main reason for that is that what we did here was we used a product to sum formula, and I'd really like to use a sum to product formula as well. Right now, the product to sum formulas just come from the sum to product formulas, or vice versa. So it doesn't really matter too much, but I would like to do it in both directions. So if you're comfortable and you don't feel like you need to see that example, that's fine. I'm just going to do the same proof. But it's kind of useful if you have the time to watch it both directions, just to kind of convince yourself that it really can be done both ways. Now, I'm not actually convinced that it can. I should give you that caveat. It can, because I could literally take right-hand side equals and then just reverse my steps. But I want to talk through the process as I go. So I'm not sure how obvious or how easy it will be to do that, but I'm going to give it a shot. All right, so this time I'm starting with the right-hand side, and that's equal to the cosine of 3x plus the cosine of x. And that is the sum of cosines of two different angles. So my formula says cosine alpha plus cosine beta equals, so my alpha in this case is going to be 3x, and my beta is going to be x. Cosine alpha plus cosine beta equals, so I can rewrite this as equals 2 times the cosine of alpha plus beta, that's 3x plus x, all over 2, times the cosine of 3x minus x, that's alpha minus beta, all over 2. I should probably point out that I don't really know what's going to come next. I've just taken what I know as the sum of the cosine of two different angles and used the sum to product rule or product formula on it. And now that I'm looking at this result, I'm going to say, oh, look, it looks like these are like terms. I can add them together. So I'm just going to do that next. I don't know necessarily how this whole thing is going to play out. I just want you to know that because as I've mentioned before, real math is messy. I could polish these, I could get them all ready for you, but I don't need to impress you. I need to teach you what the process of working a proof is like, right? And it's not always super straightforward. So even though it kind of looks like I just know what I'm doing here, and I just the next step sort of just falls out. It falls out because I'm just taking one step at a time and recognizing something in the pattern of of the trace that I've left. So what I'm going to do next is simplify what I have in my parentheses here. 3x plus x is 4x. 3x minus x is 2x. That's just algebra. I can further simplify what's in the parentheses. 4x divided by 2 is 2x. 2x divided by 2 is x. And that is also algebra. I'll also point out that sometimes, and you don't always, you're not always aware of this, but sometimes if I'm not really sure what I'm going to do next, I'll stop recording and think about it for a minute. And that's exactly what I did here. For some reason, it just didn't jump out to me, but it's jumping out to me now. This is a double angle. So I'm going to try changing the form that this is in. I'm going to try changing the cosine of 2x into the other form, the other side of its identity. This is cosine of 2x. So I'm going to have 2 times the cosine of 2x. Now there are different forms that the cosine of 2x can take, and it looks like, if I look at this, so this time I'm starting with the right-hand side, and this is my goal, right? And I can see it's buried, but I can see I have a cosine squared in here and a sine squared. So if I think of this as cosine squared minus sine squared, then that tells me that's probably the form of the double angle formula for cosine that I want to use. So 2 times the cosine of 2x is the cosine squared of x minus the sine squared of x. And that is the cosine of, let me use a highlighter, that's the cosine of 2x. So I've replaced that with this, but I still have to copy down times the cosine of x. Now if I distribute this, let's say that this is double angle formula. That's what it was, double angle formula. Now I'm going to distribute the cosine. So I'm going to have 2 times, have I missed something? Looking at cosine, no, everything's okay. The cosine, I'm going to distribute the cosine. So I'm going to have cosine squared times cosine, which is cosine cubed of x. I better keep my parentheses. Minus the cosine of x times the sine squared of x. And then I'm going to come back up here and compare that. And that's actually my answer. That's my left-hand side. So, and it's even in the right order this time. So now I can just write equals left-hand side. So that one actually wasn't too bad. I do need to make a note that what I did here was just algebra. You can write, if you want, distribution. You can write, let's see, what did we do here? Simplify fractions, reduce fractions. Instead of algebra here, you can write combined like terms. If you want to be specific, that's fine. I've said you only have to write algebra if it's something that we learned before this course. You may be more specific if you want to, but you don't have to. With things we're learning in this course, I want you to be more specific. All right, so far in this chapter, we have learned about what trigonometric identities are and how they're different from just any old equation. We've reviewed our fundamental identities, which are things like the cosecant is 1 over the sine, and the tangent is sine over cosine, things like that. We then learned about some sum and difference identities in section 2. In section 3, we talked about double angle identities, half angle identities, and reduction formulas. And in section 4, this one, we talked about sum to product and product to sum identities or formulas. That is all the formulas and identities that you're going to get as things you have to memorize or things you have to be familiar with, things you have to know about. Formulas that you have to know exist so that when you're presented with something that looks like, for example, this right here, you'll recognize it as the cosine, the product of cosines of 2 different angles, and you'll know, oh, that's a product formula. I might be able to use a product to sum formula. So that's the level of familiarity I expect you to have with these. There are 2 more sections in this chapter, so there's more work to do here, but the good news is we're finished learning all the different formulas that you need to have access to. So I would encourage you very strongly at this point to go back and make a list of all of those formulas. You'll find them in gray boxes. They are all in this chapter. They are sprinkled throughout other chapters as well, but all the formulas that you need are in this chapter, starting in section 1 with a summary of the fundamental identities. So flip back through chapter 7 up to this point and make a list of all of those. Nice, neat, sort of concise list all in one place that you can refer to. If you can get that all on one side of an index card, I would encourage you to do that, primarily because you're allowed to use an index card during tests and things. So you may want the other side for other mnemonics or other things that you might want to have access to. All right, so this is a long video. If you stayed to the end, thank you for listening to my little rant and suggestion about getting these all on a sheet of paper. And I will see you in the next section, which is about solving trigonometric equations.